Substances exist in three different phases: solid, liquid, and gas. Heating and cooling a substance can transform it from one phase to another. Vaporization is the phase change that occurs when a liquid is transformed to a gas. Substances require a specific amount of heat to undergo the physical changes necessary to switch phases. The energy or heat consumed per unit mass during the vaporization of a liquid is called heat of vaporization or enthalpy of vaporization. To condense water vapor to its liquid phase, energy must be removed from the gas. The energy per unit mass required to condense water vapor is equal to the heat of vaporization. Water in a teapot undergoes an increase in temperature when heat is provided by the flame of your stove. Let's say we heat 1 kilogram of room temperature water to boiling in a teapot. In this graph, the temperature of 1 kilogram of water is plotted against the amount of heat absorbed. The graph shows three distinct parts. Part 1. First, the temperature increases from room temperature to 100 degrees Celsius when boiling begins. Part 2. At this point, energy continues to be absorbed, but the temperature remains at 100 degrees. This is the case when the physical characteristics of water change in order to be transformed to vapor. The consumed heat is utilized to drive those changes. Part 3. After all the water is transformed to vapor, steam, the energy absorbed by the vapor is used to increase the temperature again. Molecules must be rearranged, and intermolecular forces such as ionic bonds, hydrogen bonds, and London dispersion forces must be broken for a substance to change phases. These changes are represented by the demand of energy. As you can see, the arrangement of molecules in solids is very different to that of liquids and gases. Molecules in a solid typically arrange in a periodic lattice, whereas in liquids, molecules do not have a periodic arrangement. Molecules in a gaseous substance move constantly, making the position hard to track. Additionally, the strength of intermolecular forces between molecules is significantly higher in solids and liquids when compared to gases. Molecules in a liquid and a solid are close packed due to strong intermolecular forces. In a gas, however, there are no intermolecular forces between molecules, and the average distance between molecules increases considerably. The heat absorbed from a burning flame is used to break the intermolecular forces in water and increase the interatomic distance between water molecules. Because energy is being used to break intermolecular forces, there is no increase in temperature when water is boiling. The vaporization of a given amount of water requires a specific amount of energy. Because different amounts of water have a different amount of intermolecular forces, the amount of energy required to vaporize water changes depending on how much water is to be vaporized. For example, vaporizing the water in a teapot requires less energy than vaporizing all the water in a pond. Therefore, the units of heat of vaporization are given in joules per gram or kilojoules per kilogram. The heat of vaporization also varies between substances because the type of intermolecular force varies between substances. For example, nitrogen will not have the same heat of vaporization as copper because the intermolecular forces are different in each substance. This table shows the heat of vaporization for some molecules. Helium, hydrogen, nitrogen, and oxygen have the lowest heat of vaporizations because the type of intermolecular forces in these substances are weaker than those of other substances. To calculate the heat necessary to vaporize a substance, the heat of vaporization is used along with the mass of the liquid to be vaporized. Here's the heat of vaporization equation. Q equals m times hv. In this equation, Q is the heat or energy required, m is the mass, hv is the heat of vaporization. For example, the heat provided during the vaporization of 2 kilograms of water is Q equals 2 kilograms times 2,256 kilojoules per kilogram. After multiplying 2 times 2,256, we get Q equals 4,512 kilojoules. Similarly, the heat used to vaporize the same amount of ethanol, ethyl alcohol, is Q equals 2 kilograms times 854 kilojoules per kilogram. After multiplying 2 times 854, we get Q equals 1,708 kilojoules. As you can see, the heat used to vaporize ethanol, 1,708 kilojoules, is considerably less than the heat needed to vaporize water, 4,512 kilojoules. That's because the energy consumed in the process of vaporization depends mainly on the quantity and nature of the intermolecular forces in the substance to be vaporized. In summary, the heat of vaporization of a substance is the heat or energy per unit mass needed to convert a liquid to gas. The heat of vaporization is affected by the type and quantity of the bonds of each substance. You can use the heat of vaporization equation, Q equals m times HV, to calculate the heat needed to vaporize a liquid. In this equation, Q is the heat or energy required, m is the mass, HV is the heat of vaporization.